In this video, we're going to show that non-determinism, while it might seem more powerful, doesn't really buy you any additional computational power for finite state machines. In particular, we're going to show that for every non-deterministic finite state machine, there is an equivalent deterministic finite state machine. We're going to show in this video that for every non-deterministic finite state machine, there is an equivalent deterministic finite state machine. We're going to prove that theorem. The proof is a little complex, but the way to start, I think, is to look at an example non-deterministic finite state machine and show what the deterministic machine looks like that does the same thing. So I'm going to work through this example here. In the part above the red line, we see a non-deterministic machine. It's not deterministic because at state A, there are two transitions labeled 0. Now down below, I've shown all the possible states, all the possible combinations of states. So there are 8 states here, showing each of the subsets of the set A, B, and C. So each of these states indicates that we could be in state A and B in the non-deterministic machine, or in state C, for example, in the non-deterministic machine. As we're executing this non-deterministic machine, we can be in multiple states at once. So, for example, on getting the first 0, we could stay in state 0, or we could move to state B as well. And so we're in state AB. So let's just go ahead and indicate that by drawing this transition here and labeling it 0. A is our initial state, because initially we're in state A alone, so we're in state A alone. If we get a 0, we go to states A and B. Now what about if we get a 1? Well, if we get a 1, we stay in state A, so I'll put the transition here labeled 1. What about if we are in state AB and get a 0? Well, if we're in state A and get a 0, we stay in state A or go to B. So we're in A or B. If we're in B and we get a 0, we go to C. So we could be in either A, B, or C on the second 0. So I'll put this transition here and label it with 0. What about if we're in state A or B and we get a 1? Well, if we're in B and we get a 1, we don't go anywhere. But if we were in A, we would go back to A. So if we're in states A and B simultaneously, corresponding to having our fingers on both these two states, and we see a 1, then we're only in state A. So that transition looks like this. And what about if we are in state ABC and we see a 0? Well, if we're in A, we stay in A or go to B. If we're in B, we go to C. So we could reach either A, B, or C. So on a 0, we stay in this state. If we're in A, B, and C all together and we see a 1, well, C, we have no place to go. B, we have no place to go. From A, we stay in 1. So we would then be only in state A. So I'm going to put a transition back to state 1, or sorry, to state A and label it with 1. Now what if we were in states A and C and we saw a 0? Well, if we're in A, we stay in A. Or go to B on a 0. And if we are in C and we see a 0, we have no place to go. So if we are in state A or C and we see a 0, we go to state AB. I believe that's correct. If we see a 1 in states A and C, we have only one place to go, and that's state A, so we'll put an edge 1 there. And continuing along these lines, if we're in state B and we see a 0, we must go to state C. So I'll put that edge there. And if we're in B, we see a 1, well, we don't have any place to go. So we're in no state at all. So I have an empty state down here, so I'll put a 1 there. If we're in state C alone and we see a 0, we have no place to go. So again, we go to the empty. This is like a dead state kind of down here. So I'll label it 0. If we're in state C and we see a 1, again, we have no place to go. So I'll also put an edge from C to the empty set labeled 1. And finally, if we're in B and C and we see a 0, we go simply to C alone. And if we see a 1, we have no place to go, so we go down here. And for completeness, we ought to ask, if we were in no state at all and we see a 0 or 1, where would we go? Well, it's kind of a strange case, but we would still be no place. So we'll put an edge right there. So if I've done this correctly, that is the deterministic version of this non-deterministic finite state machine. One thing I want to notice, though, is that notice that there's no way to get to state AC. Okay? So we could effectively remove it without changing the nature of this machine. And also notice that we have a component here that's completely unconnected. So we could remove this, states B, C, BC, and the empty, because there's no way to reach these states from the starting state, so we don't need those states as well. And so all we really need are these three states. Here's our theorem that we're trying to prove. Every non-deterministic finite state machine has an equivalent deterministic finite state machine. In other words, if you have a non-deterministic machine, we can build an equivalent deterministic machine. What do I mean by equivalent? Well, just that it recognizes the same language. So it does the same thing. I should also point out that for every deterministic machine, there is an equivalent non-deterministic machine. It sort of goes without saying because every deterministic machine is sort of by default a non-deterministic machine. So this two-way theorem means that there's no difference in power between non-deterministic finite state machines and deterministic finite state machines. The more complex direction, of course, is to show how to get from non-determinism to determinism. Okay, and we're going to show that and prove the theorem by construction. In other words, given a non-deterministic finite state machine, we're going to show how to build an equivalent deterministic finite state machine that accepts the same language. Let's start off by assuming that we're given a non-deterministic finite automaton, and it's characterized by a set of states Q and a transition function delta, initial state, final states, and so on. The machine we're going to construct will indicate with primes. It'll have a different set of states, a different transition function, and because its set of states is different, of course its initial state will be different, and its final states will be a subset of Q prime. So this is the deterministic machine we're building. This is the non-deterministic machine that we are given. The alphabets, of course, will be the same. We can start with a set of states. We'll assume that the deterministic machine has one state for every possible set of states. So we use the power set notation here to indicate the set of all subsets of Q. And if the non-deterministic finite machine has k states, then we'll have 2 to the k states in our deterministic machine. The tricky stuff is in the transition function, but let's take care of the initial states and the final states first. The initial state of our deterministic machine that we're constructing will just correspond to the initial state of the non-deterministic machine. So if this is our non-deterministic machine with its 3 states A, B, and C, then our deterministic version, M prime, will have as its initial state the state that's just the subset containing A itself. For final states, well, if, for example, our non-deterministic machine has final states B and C, then in the deterministic version, any state that contains a B or a C has to be a final state. So this state, that state, this one contains B, this contains B and C, this contains C, this contains B and C. So almost all of the states in our deterministic finite state machine are final. And we say that formally. It's a set of it's a set of states that contain an accept state from the original non-deterministic machine. Now, let's look at the transition function. We're building a new transition function, delta, and we're building it out of a transition function for the non-deterministic machine. We're assuming that it maps from a state in the deterministic version, which is essentially a set of states in the non-deterministic machine. So for example, we might ask, where do we go from state AB on some alphabet symbol like A? Well, AB is a set, capital R. And we say, well, we go to a set of states. We go to a set of states, Q, from the original machine, the non-deterministic machine, such that that set could be reached in the non-deterministic machine from one of the states in capital R. So for example, if there's an edge from B to C in the non-deterministic machine on A, then we'd have to go to some state that contains that. Okay, contains a C. So we build a set of all the things that we were able to reach in all the states that we're able to reach in the non-deterministic machine, and that set of states corresponds to a set of states or a single state in our deterministic machine that we're building. And we could say it this way as well. We look at our non-deterministic machine that we're given, and we say, where can we go on an R, little r, from one state on an input symbol A? Take the union of all those places for all possible states in big R, and that union is where we can get to in the deterministic machine we're building. So let's try to look at this as an example. Let's assume that our non-deterministic Turing machine has these edges in it, and we're asking, so we know that on a 1, if we're in state B, we go to states B or C, right? We stay in B or we go to C. If we're in a C, on a 1, we go to either A or we stay in C. So now we're building a deterministic version. Okay, so in the state BC, on a 1, where do we go? Well, we have to union these things. We go to BC and we go to AC. So the result is, we can, if we're in B or C and we get a 1, then we're now in either A, B, or C. So we say A, B, C. So this is the set, or the state we are labeling ABC. We've left something out, though. We've left out epsilon edges. Consider a state in the deterministic finite state machine that we're building. It's got some states in it, like B, C, E. This is the state R, and it really is a set of states from the non-deterministic finite state automaton. Now look back at the non-deterministic finite state machine and ask yourself, what states could we reach by just using epsilon edges? Because if we're in B, C, or E, we could always follow an epsilon edge. So maybe this is what our non-deterministic machine looks like. And so we're in state B, C, or E, but we've got some epsilon edges. I mean, we could also get to D, or G, or even H. And from B we could get to C, but we're already in C. So what states can we reach with just following epsilon edges? And so if we're in state B, C, and E, we should also be in D, G, and H. So what we're going to do is we're going to define a new function to handle this called epsilon closure. Okay, so we can ask, what is the epsilon closure of a set of states? So let's say we've got our set of states B, C, and E. What's the epsilon closure? If we're in state B, C, and E, where else could we be? Well, as I said, we could be in D, because we could get there from C or E. We could be in G, and from G we could get to H. So we have to include H as well. But there's no further epsilon edges, so that's the limit of how far we can go. So we can reach B, C, D, E, and G, and H. We can reach B, C, and E because we're already there. And we can also reach D and G by taking one epsilon edge. And we can reach H by taking an entire pathway of epsilon edges. So these are all the places we can reach from B, C, and E. So this function, the epsilon closure, is applied to a state in the deterministic machine we're building. Okay, I've symbolized it by drawing a circle around it. And it leads us to another state in the deterministic machine we're building. Now that we've got the epsilon closure function, we need to incorporate it into our definition of the transition function. And so this is almost the same definition as before, only we've added the epsilon closure. So we're saying that if we're in some set of states, big R, then we ask from all those states, where could we get to? And from those places, where could we get to by following epsilon edges as well? So any state we could reach by taking the transition function in the non-deterministic machine and then some epsilon edges if they exist, any place we could reach that way is something we could reach. So we have to put that in the transition function we're defining. We also need to modify the start state in the deterministic finite state machine we're constructing. So we not only start in the initial state, but we need to start in any state we could reach from the initial state. So we need to apply it that first time as well. And that is the end of our proof. Okay, so what we've concluded is that for every non-deterministic finite state machine, we can construct an equivalent deterministic finite state machine. And we've shown how to do it. Our proof was a proof by construction. We basically showed how to convert a non-deterministic finite automaton into a deterministic finite automaton. In this next section, we're going to look at an example and try to work through this and see exactly how it works. So here is a sample non-deterministic finite state automaton. Doesn't really matter what it does, but you see we've got 3 states and we've got some epsilon edges. We have one epsilon edge. It turns out the initial state is the same as the final state. The input symbols are A and B. So let's begin our construction. First we need to ask what states are going to be in our deterministic finite state automaton. Well, that's the power set of these states. And here I've listed every possible set of these 3 states, including the empty set. So these are the 8 states we'll have in the deterministic machine we're building. Let's start with the start state. Well, we need to we start in state 1 in this thing, and we also need to take the epsilon closure, so we could reach 3 immediately. So our definition says take state 1 and apply the epsilon closure, and that's the set 1, 3. Well, I prefer to put circles around these, and I'm going to show in blue the states from the non-deterministic machine that were given, and I'm going to show in red the states from the deterministic machine that we're constructing. So from this state in the non-deterministic machine, we take the epsilon closure of it, and that leads us to states 1 and 3, and so that's going to be our initial starting state in the machine we're building. What about the accepting state? Well, our accepting state is also 1, so any one of these states that contains a 1 has to be a final state in the machine we're building. So 1, 1, 2, 1, 3, and 1, 2, 3. I've repeated here the non-deterministic machine that we're given, so you can see it. And we're now ready to build a transition function. For each state in the deterministic machine we're building, we need to have two edges, since our alphabet has an A and a B in it. So we need to find out where we're going to go on an A and where we're going to go on a B. So let's grind through this and see if we can work it out. We'll start with the state that is just 1. If we get an A, let's look at this. If we get an A, where do we go? No place. If we get a B, we go to 2. So, since there are no edges labeled A, leaving 1, we go to the empty state, if you will. And from 1, if we get a B, we go to a 2. And there are no epsilon edges out of 2, so we stay there. We don't add anything. From 2, if we get an A, let's see where we go. If we're in 2, we get an A, we stay in 2, or we can go to 3. So 2, 3. If we get a B, we go to 3. So 2, 3, and 3. Now what about if we're in state 3 and we get an A? If we're in state 3 and we get an A, we go to 1. But we can also take an epsilon edge and get back to 3. So we can be in state 1 and state 3. So let's put that down here as state 1, 3, because we can get to 1, and then from 1 we can get to 3 by following an epsilon edge. Okay, here's the final result. I've repeated the non-deterministic machine that we're given there, and continuing along in the same way, this is the final result of states and edges in the deterministic machine. And you can see it's grown quite a bit, but I assert that it does the same thing, that this machine is equivalent, which means it recognizes the same language, the same set of strings. And one thing to note about this is that state 1 is unreachable, and state 1, 2 is also unreachable. So we can safely remove these states from our machine without changing its functionality. But the other 6 states are necessary.